Okay, welcome. We're going to discuss the chapter 3 and 4 chapter review here. The first thing that it talks about is states, and we have 3 states of matter that we talk about in this course: solid, liquid, and gas. A solid has a definite shape and a definite volume. And you can find the volume. You can do water displacement for that. You can measure it. Like if it's a block, you could go length times width times height. And then the shape is definite. It doesn't change. So if you set something down on a table, it's going to maintain that same shape. Now, liquids have a definite volume, but their shape is variable, and it varies based on the container that they're located in. And gases are variable in both their volume and the shape. So those are characteristics that you can use to determine if you have a solid, liquid, or gas. Phase changes then are the next thing that we talked about. With these phase changes, when we look at those, we're looking at the first one is a solid to a liquid, so that would be melting. We have a liquid to a gas. That can take place in 2 different ways. We call both of those vaporization. One of them is a very slow process, which is evaporation. And the other one is a more rapid process, which we call boiling. We also can talk about a solid to a gas. This is called sublimation. A liquid to a solid is freezing. A gas to a liquid is condensation. And a gas to a solid is called deposition. So in these processes here, we're losing energy. In these processes here, we're gaining energy. All of these are phase changes, and all phase changes are physical changes. Then we wanted to know the difference between intensive and extensive properties. Intensive, it does not matter what the sample size is. It's irrelevant. Extensive, it does matter. It changes how much you have. An intensive property, we could list several of those. A boiling point is one of them. Melting point. So if we talk about water, for example, the boiling point is 100 degrees Celsius. It doesn't matter if you have a 5-gallon bucket of it or 2 tablespoons. The boiling point is still 100 degrees Celsius. Melting point's the same way. That ice is going to melt at 0 degrees Celsius, no matter if you have a small chunk of ice or a huge chunk of ice. Now, it's going to make a difference in how long that takes to melt all of that away. But that boiling point, the temperature that happens, is the same no matter how much you have. Density is another good example of an intensive property. Extensive properties, they vary based on how much you have. So mass, for example, if I have 1 milliliter of water, it's going to have the mass of 1 gram. If I have 500 milliliters of water, that would be 500 grams. So that makes a difference how much I have. Volume, length, width, height, all of those are going to be extensive properties. Here we wanted to know how many of each atom, or how many atoms we have in each of these compounds. This one, we have 1 for our lead here. This we have to distribute between the numbers here. So the first one will be 2 times 1, which is 2. And the next one, we would have 2 times 4, which is 8. So that gives us a total of 11 atoms in that compound. Here we have 1 atom of calcium and 2 of chlorine for a total of 3. Here we have 6 carbon plus 12 hydrogen plus 6 oxygen. So it's going to give us 24 there. And here we have 1 and 3, so that is going to make 4. Filtration then is the process where we use differences in particle size, and we use filter paper. So using filter paper to separate mixtures based on particle size. Chromatography then, we are going to use chromatography paper to separate dye mixtures based on their ability to mix with a solution. Distillation then uses the difference in boiling points to separate mixtures. And then finally, crystallization. We're going to separate solid particles by evaporating off a liquid. Okay, so if we go out and we look at, let me see if I can pull a video over here, or image is here. So filtration. The idea with filtration is that we are going to, we typically will have some sort of filter paper in here. We're going to separate out a lot of times solid particles here from liquid particles, and they're going to be left behind. You can kind of see a close up here where if you had a piece of filter paper here, it would capture these larger particles, but the smaller particles would still be allowed to go through. When we talk in terms of, I think distillation was the next one that we were talking about. When we look at a distillation apparatus here, you're going to have a solution down in here, 2 different solutions. One of them is going to have a lower boiling point than the other. So if you heat this up, one of them will boil before the other. It'll then capture the gas from that. It'll go down this tube, and then this tube has around it, surrounding it, cooler water that's cooling it down and causing that material to condense, and then that'll be in the liquid form over here. So that's how they're able to take advantage of that. Chromatography then, when we look at that, typically they will have taken dyes and put on a piece of filter paper, and then they're able to let water or some other soluble liquid move through that. It'll move up through here, and then these dyes have different molecular masses and different attractions for that water, and so it'll be able to separate out those dyes based on that. And then the last one was crystallization, and here you will have a typically a liquid in here. That's probably not the best image of that. You guys have probably done this in like elementary school. Yeah, here we go. Where you had typically a string that's here. You've got a material down here that has some sort of solid dissolved in it. And over time, the solid will get left behind on this string, and that leaves the liquid down in here. So that's one of the ways that they're able to do crystallization. When we talk about chemical versus physical properties, chemical properties are those properties that are going, when the material is acted upon, they're going to change the identity of that substance. Physical properties do not change the identity of the substance. So mass, well, here's examples down here, I guess. So difference between chemical and physical properties. Chemical properties show how a substance can change into another one. Over here, they're properties that describe the substance and no change in identity occurs. Examples of chemical substances would be flammability, corrosion, trying to think of tarnishing. All of those would be examples of chemical properties. Physical properties, you could have mass, color, so those just go on and on. Volume, any of the ones that we listed up above when we were doing the extensive, intensive, all of those would be physical properties as well. List the parts of an element that is listed on the periodic table. So I believe that's in reference to this. This number right here is called the atomic number. That is also the number of protons. This is, of course, the name. We have the symbol here for, and then this is the average molecular mass. This would also indicate what phase it's in when it's at room temperature. And then next chapter, we'll get into what these things are. You don't need to worry about those right now. If we were to draw a lithium atom with 3 protons and 3 neutrons, the protons and the neutrons, remember, are in the nucleus. So I'm going to do the protons as a dot and the neutrons as a circle. So there's my nucleus. I would have 2 electrons out here, and I would end up with 1 electron out here. And we'll talk more about how many are in each shell and that sort of thing when we get to next chapter. What is the atomic mass of this? This would end up being 7 for its atomic mass because we have 3 protons and 3 neutrons. Then they want me to complete this table. So we're dealing, I need to shrink this down a little bit so we can get it all on here. Okay, there we go. So if we have a mass of 28 and we know that this is element 13, we're going to look on our periodic table, find element 13 that identify as aluminum. If my atomic number is 13, that means that I have 13 protons. It also means that I have 13 electrons because this is an atom. We have the positive and negative charges are going to be equal to one another. Then we need to figure out our mass. So our mass is our protons plus our neutrons. So if we know the mass and we know the protons, we just need to subtract those protons from the mass, and that will give us the number of neutrons in that atom. Copper, we have 66 protons. We need to look up copper's number on the periodic table, and it's 29. So we also have 29 electrons. And if we take 66 minus 29, that's going to give us 37 neutrons. And again, our atomic number equals the number of protons. So that's going to be 29. So atomic number is protons. That's how many protons you have. Your mass is your protons plus your neutrons. All right. Our next one, we have 19 electrons, which means we have 19 protons. Our atomic number is also 19. Number 19 on your periodic table is potassium. Its symbol is K. And if we have 40, we have 40 minus 19. That means that we have 21 neutrons. All right, down below, we're going to be heating our calcium carbonate. And I have to make this a little bit smaller again. We're doing our calcium carbonate here. We have, we're heating this. We're forming 4.4 grams of carbon dioxide, and we're also forming 5.6 grams of calcium oxide. So that means that if all of that came from here, which they said it did, all we have to do is add those two values together, and that's going to give me the mass of how much I started with, because according to the conservation of mass law, the materials that we start with have to equal the materials that we end with. All right, then they wanted to know the percent composition for lead sulfate. So if we do that, we need to find out the mass of one of our lead. So we have one lead. And we find on the periodic table, lead's mass on the periodic table, which is 207.2. We have 2 sulfur. Those are 2 times, so this is sulfur, 2 times 32.1. And then we have 8 oxygens. So that's 8, sorry, hold on. We have oxygen. We have 8 of those times 16. And we're able to figure out our amount for that. So let's grab our calculator here. We can crunch this number without any assistance, but the next one would end up being 64.2. And then the last one, 8 times 16. 8 times 16 is 128. So those are my parts. I'm going to divide them by my whole. So now I'm going to grab this. I'm going to add all of these values together to get my whole value. So 207.2 plus 128 plus 64.2 gives me a total of 399.4. I don't know how great that pen color is showing up there. That's still not much better, is it? I was trying to do it in a different pen color, but it doesn't look like it's going to be showing up well enough. So I'll go back to the red. So I'm going to divide all of these by the total mass here, which is 399.4, multiply by 100, and that's going to give me my percent for each one of these. So the first one here ends up being 51.9%, 51.9% lead. The next one is 64.2 divided by 399.4, and that's 16.1. And that is percent oxygen. And the last one ends up being 128 divided by 399.4, and that's 32.0. And that is percent, oh, this is a percent oxygen. I'm sorry, this one back here was percent sulfur. My apologies. This was percent sulfur. There we go. Okay, so remember that when we get done here, we should be able to add up these values, and they should end up coming out to be about 100%. So it's a good double check of your work. The next one is an average atomic mass. So we're going to have, we've got two different types of this isotope. We have one with this mass, so 31.868, and it says that that one I have 88.34. So I'm going to take that out of decimal form or percent form, put it into this form by dividing by 100. And then I have this guy, I have 0.1166. I just took that out of form by dividing by 100, and I'm going to multiply it by its mass, which is given here, 34.838. Now, before you even get started with these, you should be able to recognize this. Since the bulk of this material is made up of this type, that means that our answer is going to be closest to this value. It needs to be between this value and this value, but it should be closer on this. If you think of like one of those number lines like you had in elementary school that they had number lines for you to draw on, the number should be closest to this value. So let's go ahead and do the calculation for that. We have 31.868. We're going to multiply that by 0.8834. And when we do that, we end up with 28.15. Over the next one, we have 0.1166. We're going to multiply that by 34.838. And we end up with 4.06. We need to add these two values together then. So I'm going to add my 28.15 plus my 4.06, and I end up with 28.15. That is my answer. And again, oh, wait a minute. I ended up getting the wrong answer. Hold on. There we go. That's better. Sorry. But that's not our answer. That was over here. I grabbed the wrong one. So if I add these two together, my apologies, I end up with, and I knew right away that I had done something wrong because it wasn't between those values. All right, so 32.21, that's our answer. And again, that's going to be between this value and this value, and it should be closer to this value than it is this one because that's where the majority of the material is. All right, so the next one is half-life. We have a 208 gram sample. It's going to decay to 13 grams in 60 hours. They want to know what the half-life is. So if I take 208 and I'm going to divide that down. So 1004, I'm going to divide that down. 552, I'm going to divide that down. 26, and that divides down to 13. So how many half-lives did I go through? I went through 1, 2, 3, 4 half-lives. It took me a total time to get from here all the way to here. It took me 60 hours. So if I take that 60 hours and I divide it by how many times, how many divisions we have here, that's going to give me my half-life. So 60 divided by 4 is 15. So our answer would be 15 hours for that problem. Here we have an 800 gram sample. It's going to decay to 100 grams, and they want to know what its half-life is. So we have 800, 400, 200, and 100. Now, how many times did we divide that? 1, 2, 3. So if those divided 3 times, we are going to take this value and divide it by 3. So 639,000 divided by 3 equals, that would be 213,000, and that's going to be years. And that would be our final answer. All right, next one. We have potassium here. Potassium has a half-life of 12.4 hours. How much of an 848 gram sample will be after 62 hours? So we're going to take this, we're going to divide it down. I'm going to go in half here. So that's going to be, 424. And it would have taken a total amount of time here of 12.4 hours. I'm going to keep dividing this until I get down to 62 hours. So I'm going to divide it again. So that would take me down to 212 here. So 12.4, so that would be 24.8 total, because I added another 12.4 to get here. So I'm going to keep going. So it's going to take me down to 106. And 24.8 plus 12.4 gives me 37.2. Then I'm going to take that and I'm going to divide it again. So that's going to be 53. I'm going to add another 12.4 to my running total down here, 49.6. And then if I add another 12.4 to that, it's going to take me to my 62. And half of 53 is 26.5. And that would be my answer, 26.5. And that would be grams. And that would be my final answer for this. All right, the next one, we are taking uranium, and they want to know what particle would have been given off of here. Well, we went from 238 to 234, so that would have been 4 here. We went from uranium, which is 92, to thorium, which is 90. So we went down by 2 for that. So that would be a helium. That would be an alpha particle then that would have been decayed. All right, so we've got this being produced. So chromium 53 was produced, and it's a beta decay. So chromium 53 chromium is 24. I guess I should have drawn that on the other side, sorry. So this is going to be 53, 24 for chromium, and it said beta decay. So we would have beta is 0 minus 1 here. And we need to figure out what our starting thing was. So if we went up a number here, or I'm sorry, if we went down, so this would have been 23. And then our mass would have stayed the same, which is 53. So element number 23 on the periodic table is vanadium. So our answer would have been D for this guy. And our last problem here on our homework, we're going to produce, this is titanium 48 is getting produced by alpha decay. So titanium, it's 48. Need to look up the number on the periodic table for that. And it is number 22. So number 22, we went down for beta or alpha decay. So that's 4 to helium. And if I look on here, this would have been 24 on the bottom, and on the top would have been 52. So which one of these has 52? Well, we're hoping that chromium is number 24, which it is. And that means that that is our correct answer. So hopefully that helped you a little bit with this review. And if you have any questions, please email me and I'll try to get you caught up.